Okay, the next question that we're going to look at for the properties involves kind of a familiar property from algebra with a little bit of an unfamiliar twist. So you'll see in the screen here that we're looking at the property. We want to prove that for any z sub n, the quantity of a plus b squared is what we expect it to be, a squared plus 2ab plus b squared. Now, I am using the bars over this again just to keep reminding us that we're dealing with a different set of numbers, that these numbers mean something a little bit different than what we're used to in algebra. So just kind of keep that in mind. So we're going to look at a little bit more general. Notice I don't have my chart this time because we're looking at this for any z sub n. And again, one of the things to kind of keep in mind here is there are some of the algebraic rules differ. Some of them are the same. The ones that tend to be the same are the ones that overlap with this notion of being a ring. And you can look those properties up on page 318 in your text. But they're basically about the things that we know: commutativity, associativity, addition, subtraction, stuff that we're fairly familiar with, but we don't want to assume too much more than that just yet. And so we can use those properties to go ahead and prove this. So basically, the first step is I can start with a bar plus b bar. I'm just going to say a and b. And just by definition of the square, we know that this is the same thing as a bar plus a plus b times a plus b. And that's just definition of what it means to be squares. Okay. Now, you may have learned the term FOIL. You may kind of skip over a step, but technically there's a step in between we need to do. And so to show this, we're going to distribute. Essentially, we're going to take that first chunk, this first one, this a plus b, and we're going to distribute it to the things that are inside the second set of parentheses. Okay, so the way that's going to look is I'm going to start by writing a plus b times a, and then a plus b times b. And that's distributive property. It's just that we're using that first binomial as kind of a chunk that we're distributing. And this is kind of the method that you probably learned. It's just this is the extra steps involved. And this is how we would actually prove it in a normal algebra class. And then the next step, of course, we're going to distribute again, only that this time we're going to distribute with those the smaller ones, the a's and the a and the b. So we get a bar, a times a, plus b times a, maintaining order for a moment. And then the next one we're going to get a, b, and then, oops, forgot my bar there, b times b. Okay. So far, so good. This is all looking great. Well, by definition, we know that a bar times a bar, just a times a, is a squared. Let's draw that carefully. So a squared. And if you remember, just from looking at our table, we know that that this is commutative. The multiplication is commutative. So b times a times b, those are the same thing. So I can combine those and group them together and get to a b. And then same thing, b squared for b times b. So essentially what we've got here is exactly what we know from algebra. And we've shown that this particular property is also true when we're dealing with the modular arithmetic, when we're dealing with z sub n. Okay? So that's the first thing to look at, that some of our properties are going to stay the same. But here's an interesting little twist that I want you to think about. So what is special about this in z sub 2? So why don't you take a minute and you can pause the video for a second and go ahead. Sorry, gotta charge my pencil. Pause the video for a second and think about that, and then come back. Okay, hopefully you thought about that. And so I'm just going to bring down this statement again. So I have a plus b squared equals a squared plus 2ab plus b squared. So the interesting thing occurs in this middle term. Because notice what is in front of the a and the b. We're talking about a 2 here. Well, in mod 2, anything divided by 2, that includes any even number, but anything that has a divisor of 2 is actually equal to 0. So it turns out that in z sub 2, 2ab is equal to 0. It doesn't matter what a and b are. Granted, they're just going to be 0 or 1 dealing with this. But we do definitely know that 2 times that is always going to be 0. So it turns out that in z sub n, or z sub 2 rather, a plus b squared is a squared plus b squared, which you probably heard many of your algebra teachers yelling at you about, say, don't ever do that, don't distribute the square, or however they described it. I've heard interesting things over the years. It turns out that in this one instance, it actually does work. But I'm going to emphasize in z sub 2. Don't go to your math teacher tomorrow and say, hey, I just heard from my number theory teacher in GOA that this is true. Because I'll be more than happy to share with them exactly where I told you it was true and that it doesn't work anywhere else. Anyway, it's a familiar property, slightly an unfamiliar twist thrown in there.